Sweet, all set and ready to record, so hooray. Any event, welcome back. So in this section, we're actually going to be looking at another topic that's going to be really closely connected to that last section. So last section was all about trying to minimize the number of cuts to actually split a network into two. Today, we're going to be looking at similar types of networks, but the question is going to change a little bit in that we're going to be interested in trying to pump as much stuff through this network as possible. So formally, this is going to be a question referred to as a flow, and we're going to have a really cool algorithm to actually try to maximize the overall flow through a particular network. So the algorithm is going to be referred to as this Ford-Fulkerson method, and what's really cool about it is that it feels very natural in that we're going to try to basically do individual little paths as we go, and then slowly kind of combine all of them together. So at the heart of this thing is simply going to be a path finding algorithm. And then we're just going to run this a whole bunch of times and then sew everything up very nicely. So down below, I got my cool little picture of this dude with this little sword from last section. So that was all about trying to look at cuts. Today, we're going to be chatting about flows. But what's really nice is that these two questions are very well connected. If you have a cut of something, it usually is going to give rise to a flow. And if you have a flow, it'll also connect back into a cut. So let's go ahead and actually chat about what this is going to look like from a picture point of view. So down below, I'm going to have a nice little flow network. Here, it's going to be 6 of your favorite Canadian cities, or maybe 6 Canadian cities that you now know the names of. I was mentioning to my in-class students that living in South Dakota is the first time I've ever lived in an area that is not directly connected to Canada. So I've lived in Minnesota, North Dakota, and Pennsylvania. So if we're including that tiny little notch by Erie as being connected to Canada through Lake Erie, then I've always lived in an area that's touching Canada, except for while living in South Dakota. So anyway, here are 6 Canadian cities, starting on the west of Vancouver and then ending up in the middle of the country in Winnipeg. So Winnipeg is directly north of Fargo, and I lived in Fargo for about 8 or so years. So we would very often drive up to Winnipeg for the weekend and then come back down. So I have a lot of good memories of Winnipeg, and we have a slew of other cities here as well. So this particular little network's got a bunch of little arrows. So the arrows are going to represent some type of transition. I can pump some resources or some goods from one city to another. Formally, those are going to then be capacities. And you can see that these flow networks then can represent pretty much anything. Anytime you have some restriction on what you can actually push through a particular channel, you naturally are going to have a flow network. If you want to think about where the name actually comes from, it's going to then be connected to various size like pipes for water. So you're going to have this thing can handle this much water, this thing can handle this much water. So if we were to let this system just go, where is the water ultimately going to land? You can also brand this in an electricity side of things. So you have different gauges of wires. So you're going to have some electrical current going through some things, and where is it naturally going to kind of pool and end up? And then let that process just snowball out of control. And then you can represent this as really whatever scenario you'd ever want. Anytime you have things that need to go from a source to a sink, you're naturally going to have a flow network. And that's exactly the notation that I'm going to use here. So Vancouver, I'm going to label as a little s, which is going to be my source. And then over on the right, I'm going to have Winnipeg, which is my sink. Unfortunately, source and sink both start with an S. So we typically write the source as an S and the sink as a T. So between those two things, you can see that we're going to have a variety of other cities, which are just going to be represented as other vertices. So you can see that Vancouver is going to have the potential to push goods up to Edmonton or to Calgary. And then from there, we can begin this snowballing process of looking at intermixings of transportation networks and all of those kind of things. So the goal is then going to be is how much stuff can I push from Vancouver into Winnipeg? Right from the get-go, you can see that Vancouver can theoretically pump out 29 resources, whatever those things happen to be, 29 blah. However, on the receiving side, Winnipeg can only receive 24 things. So somewhere between those two things, there's going to be a cinch point that I'm going to lose some stuff. There's going to be some loss that's then going to be incurred. So our goal is then going to be to try to identify where that is actually going to occur, as well as how can we possibly overcome this. You can kind of see initially the goal is going to be to try to get 24 things to Winnipeg, which is actually not going to be possible in this network either, in that we're going to be further restricted by some of the movement along the middle. So that's our big goal, is then to take one of these little networks and try to maximize the amount of stuff that we're going to be pushing through this. Here's a cute little example with two, a single source and a single sink and only 4 in between bits. Obviously, you can make this much larger, and then those questions of efficiencies and how we're actually going about this are going to matter tremendously, and that's where the game gets really fun. I said the word game, which really is how I like to think about these things as well. So I'm a huge board game nerd, and I love all things Euro games. And most of those games all have this idea of take resources from one location, bring them to another location, turn them into additional commodities, take those commodities and then bring them from one location to another location, and rinse and repeat that process over and over. So half of those games are just some big epic flow network that you're trying to move things as efficiently as possible, and that you're limited by something. So that's the idea, is that we're limited by, or we have expensive paths that we have to go across, and we're going to try to play the game of doing things as efficiently as possible. Cool. So here's what I just mentioned in terms of my outflow and my inflow. So our big goal then is going to be, how do we actually begin moving some stuff around? So I want to kind of spend just a couple seconds chatting about kind of a big picture idea, and then we're going to go into the technicalities of how this is actually going to work. But what's really cool about this process is that it does feel kind of like what you would want to do. Is basically, you would look back at this big network and you'd be like, well, across the top, I could theoretically send 12 goods. I'm limited by that middle value, but I could send 12 of the 16 there, and I could send 12 of 6 or 12 of 12 there, and I could send 12 of 20. And that's going to be the notation that we're going to use as well. So the thing on the right is going to represent our capacity, or how much we could send. And then the thing on the left is then going to represent how much we are actually sending. So here you can see that Vancouver to Edmonton, there's 4 missing pieces because I'm using up 12 of the 16. Same thing into Winnipeg, I'm using 12 of the 20, so I have 8 in reserve. That would then represent some movement of 12 goods. But I could also do a little bit better. I could actually think about, okay, I'm going to send 11 down the bottom, and I can send 11 across this bottom, so from Calgary to Regina, and then I'm going to split those 11s. I'm going to then send 4 of them up to Winnipeg, and then I'm going to send 7 of them up. And then I actually have to fix my 12 in that 12 is now going to become a 19. This is actually going to become our optimal flow in this, but we want to begin chatting about systematically doing what we just did there, because it's easy when it's a little graph of 6 vertices. That process becomes a little bit more complicated when we switch this to 20,000 vertices, but the same feels should be existing in the background, is that we're going to do this essentially one at a time. We're going to go across the top, maybe go across the bottom, and then begin kind of running this greedy approach over and over and over again and seeing what's going to happen. There's a couple other comments I want to make before we go too far into this, in that this network is somehow stable, in that everything is balanced. So every one of those middle terms have a balance of inflow versus outflow. So if I think about these properly as being zeros, you can see that up at Edmonton, my inflow is 12 plus 0, which equals my outflow, which is 12. Down at Calgary, my inflow is 11, technically plus a 0, which is then equaling my outflow, which is 0 plus 11. In Regina, where I actually did the little split, you can see that that does actually work out. So I'm going to have 11 is then going to be 7 and 4. And then up in the top, I'm going to have, 7 and 12, which makes my 19. So everything is nicely stabilized. Inflows perfectly match the outflows. That's going to occur in all of the middle cities. Technically, on the outer side of things, they don't have one of them. So Vancouver is only pumping goods out. So officially, it's going to pump out 23 things, which matches what Winnipeg is actually receiving. Winnipeg is receiving 19 and 4, which is receiving 23 of them. So notationally, I'm going to say that I've just created a flow F, and the total amount of goods that this flow can then send out is then going to be given by 23. So we're just going to slap on some absolute value bars to chat about the actual amount that's going on. So down in the notes, I have a few other just little comments about the technicalities of what we just said there. So the inflow versus the outflow, that's just a matching of those two little sums. So you can put it with fancy little things as well. Technically, we're going to have a capacity constraint, which is just when I make these little fractional things, I don't want to exceed the overall capacity. So when I chatted about, 12 of 16, I can't chat about 18 of 16 or anything like that. So I have two big requirements. I need everything in balance. So this conservation of electricity or goods or whatever you want to think about it, as well as some type of capacity constraint. So then the formal question that we're going to pose then is, how can we maximize this flow? And then in fact, what is the maximum flow? So that's our big goal in all of this, is to solve this maximal flow question. And what's really cool about this is that if we go back to the hand-drawn one that we did before, there's some beautiful connections between this maximal flow question and a cut question. If you look down at this little network that we have, you can see pretty obviously where some capacity requirements are being achieved. We have a capacity achieved here, here, and here. And if you look at that long enough, you can kind of see that those become the key components of this network. If you were to increase the capacity anywhere else in this graph, you would not increase the flow at all. So if you have this Vancouver to Edmonton and you're like, well, what happens if I can actually increase that from a 16 to a 17? Maybe if I can pump a few more goods up there. You'd be like, cool, that's great. I can't do anything with that though. So if I change that 16 into an 18, I can't get anything extra out of it. If you change any of those values along that purple route though, you would actually possibly increase your flow. So those are going to be kind of the key ones, which then becomes this like terrible debate at some industry of being like, well, let's pump more goods from Vancouver to Edmonton. And you're like, well, that doesn't help at all. We need help along these three purple routes. If we can improve those, then we can actually improve the overall flow as well. So you can see that those purple ones essentially are going to highlight some type of cut in this little network. And then that becomes this nice connection between cuts and flows. And we'll keep on bouncing on that back and forth a little bit after we kind of jump into this overall network kind of design. So I'm going to pause it there, and then we're going to start chatting about the actual notion of augmentation. So there's going to be some cool little topics about how do we find these paths and what do we do with them. And then we're going to run this full-fledged Ford-Fulkerson method, starting off with a zero flow and then building this thing up as we go. So we'll give this a nice little pause, and I'll come right back.